So let's keep going on finding our directional derivatives. And this derivative is going to be a little trickier for us to find. So we need to find the derivative with respect to x. Now this is a quotient, so we're going to need quotient rule in order to find the derivative. Or we could use product rule if we rewrite it with a negative power, but that's just cheating. So quotient rule, you take the denominator, you write it and square it, and then you take the denominator and write it out front. Then you multiply by the derivative of the numerator with respect to x, which would be 1 minus. Then you write the x, the numerator, and you take the derivative of the denominator with respect to x, which would be 1. So that leads us x minus y minus x over x minus y squared. Of course, the x and the negative x are gone, because x take away x is gone. Boom. And that leaves us minus y over x minus y squared. Now, that is the general derivative of f with respect to x. But of course, we want it at a particular point. Let me put this in a different color here. So we want it at 4, 1, because 4, 1 was the particular point we are looking at. So let's put that in. At 4, 1, what we're going to get is f sub x at 4, 1 equals negative 1 over 4 take away 1 squared. That's 3. So 3 squared is 9. So negative 1 over 9. We will keep that in mind for later. All right, now we have to do it again. F sub y is, and again we have to do the quotient rule, so x minus y squared. Now the derivative of the numerator with respect to y is 0 because there is no y term, which is going to make things nice and easy. And then we write the numerator x, and the derivative of the denominator with respect to y is negative 1. So this whole term is gone, right? So that's 0. So this ends up being x over x minus y squared. Now, at 4, 1, f sub y at 4, 1 would be equal to 4 over 4 minus 1 squared, which is 4 over 9. Okay, so putting these two pieces together, we now know that the gradient of f is negative, the gradient of f at the point 4, 1, because of course there's lots of different gradients of f. This is at this particular spot. The gradient of f with at 4, 1 is negative 1/9, comma 4/9. Okay, now what about our unit vector? Our unit vector is this direction. So we know we need to go in the negative 1, 2 direction. But in order to make it a unit vector, we have to divide by the magnitude. 1 squared plus 2 squared, which is 4 plus 1, which is 5. So that makes it negative 1 over the square root of 5, 2 over the square root of 5. All right, so for the final result, the directional derivative of u, or excuse me, of f in the direction of u at the point 4, 1 is equal to the dot product of negative 1/9, 4/9 with negative 1 over the square root of 5, 2 over the square root of 5. Negative 1 times negative 1 is positive 1. So that's 1 over 9 square root of 5 plus 8 over 9 square root of 5. 1 plus 8 is 9 over 9 square root of 5, and the 9's cancel, and we're left with 1 over the square root of 5. And if you want to rationalize it, it's the square root of 5 over 5, but it's not important. All right, so now keep in mind, that's the directional derivative at this specific spot and going in that particular direction. There's lots of different directions you can go and lots of different spots you can take. So this was the gradient right here, but then I put in those particular values because that's the point I'm working with. All right, let's do it again down here. So we're going to find the Oh, and I guess I could say the generic gradient of f, if you want it, is negative y over x minus y squared, and then x over x minus y squared. That's the gradient in general. And the gradient at this particular spot is these two numbers, right? So they're both useful. All right, so let's find the gradient on this one. This will be easier actually. It doesn't need quotient rule. All right, so the gradient of f would be equal to f sub x, f sub y, f sub z, which luckily for us is really easy to find because you pretend like the y and the z's are constants and you just take the derivative with respect to x. So it's 2x and then yz cubed. And then pretend the y is the only variable. So it's x squared z cubed because the derivative of y would be 1. And then it'd be 3z squared times this other stuff. So 3x squared yz squared. All right, so this is the generic gradient. Now I want it at the particular point we're looking for. So 3, negative 1, 1. Right, that's our point. So then we're going to find the gradient of f at, oh, I could do it at with the vertical line, or I could do it with parentheses. It doesn't really matter. 3, negative 1, 1, which is equal to, okay, so we're going to start substituting. 2 times 3 times negative 1 times 1 cubed. I'll put parentheses around the negative 1 there. And then 3 squared times 1 cubed. And then 3 times 3 squared times negative 1 times 1 squared. All right. So that's a negative 1 times a 2 times the 3. So that's negative 6 in the front. This is 9 times 1, which is 9. And then 3 times 3 squared is 3 times 9, which is 27. And then there's a negative, so it's going to be negative 27. So that's the particular gradient at that particular point, as opposed to the generic gradient, which is the gradient anywhere. All right, now I need my direction vector, u, which was in the direction of 4, 2, 3. So I need to take 4, 2, 3, and I need to divide it by the magnitude in order to make it a unit vector. And that's 16 plus 4 plus 9, which is 29 again. So we've run into that one before. So this is 4 over the square root of 29, 2 over the square root of 29, and then 3 over the square root of 29. So then for the directional directional derivative of f in the direction of u at 3, negative 1, 1, we're going to take negative 6, 9, and negative 27, and we're going to dot product that with 4 over the square root of 29, 2 over the square root of 29, 3 over the square root of 29. All right, so negative 6 times 4 is negative 24 over the square root of 29, plus 18 over the square root of 29, and then 27 times 3 is 81, so minus 81 over the square root of 29. And putting these three together, they almost cancel each other out. We're just left with 6, so it's minus 87 over the square root of 29. We don't quite have a good visual sense of what this means, per se, because it's in 3 dimensions, but we know we can still find it, even without that strong visual sense of the ceiling piece. That ceiling piece really works for f of x, y, not so much for f of x, y, z. But we know that the math checks out and can be extended.